All right, so I'm Andrei, XJ Technologies, and now the AnyLogic company, vendor of AnyLogic simulation software, and this is, you can consider this like a big lecture about what is simulation modeling, where it is applied with some examples, some live model building, etc. So its general topic is how simulation modeling is used for business applications. So a few words about the company. We're a stem off of St. Petersburg Polytechnic Institute, now the Technical University. We do two things. We're a software vendor and we do consulting services. The main major revenue comes from software licenses, about 70 to 80%. So you can consider us as mainly software people more than consulting. AnyLogic is sold worldwide, and at the moment we have about 700 commercial organizations using AnyLogic and more than 1,000 universities using AnyLogic for teaching. It's a general purpose simulation modeling tool used across many areas. Logistics, transportation, supply chains, I'd say this is like area number one where it's used, especially in Russia, if we take Russian markets. Healthcare is number two. That's mostly international, United States and Europe, not really zero users in Russia. And then manufacturing, various kinds of service systems, military defense, any kind of strategic planning, etc., etc. So geographically, the development team is here in St. Petersburg. Then we have two branches in Paris, and we're now moving in the United States to Chicago area, and a number of distributors. So that's kind of geography of our users. The biggest user group is here, like about 40%. Then Russia, Europe, Asia, it's like about 10 to 15% each. As I'm saying, we have a very, very diverse user base, and if you look here, you can find companies, in the range from like insurance, banks, defense, transportation, supply chains, all sort of stuff, pharmaceuticals. So this is the agenda for today. We have two parts and a break in the middle. Part one, theory. So what is simulation modeling? What kind of simulation, what is modeling in the first place, and then what is simulation modeling. I will be building some toy models in front of you, and we'll be discussing you how they work, that sort of stuff. Then I think we have a half an hour break, and then the second part is like more industrial examples, more demos of models that we've built or our clients have built. And please, guys, do make this as interactive as possible. So questions are welcome anytime except for the break, because the break is a kind of sacred time for the lecturer to get some rest and to prepare for the second half. So interrupt me at any time. If something is just trivial for you, tell me. I'll skip it. If something needs more explanation, just raise your hand and go ahead with your questions. All right, so part one, theoretical part. And I always start with this slide about modeling, because this is really the slide I love. So you have a real world, and you have a problem in the real world, and you're looking for the solution. But in many cases, it happens that by doing things with the real system, experimenting, changing, building new stuff, it's not possible to search for the solution because it may be too risky, too expensive, or the real thing may just not exist. And then what we do, we go up from the real world to the world of models. We build the model of the system. This is the process of abstraction. While building the model, we throw away things that we think that are not important for solving this particular problem. We leave things in the model which we think are important, that they matter. This is really very, very informal process, and I'd say this is, to date, is more art than science or technology. So we've built the model. With the model, we do things. We do calculations, simulation, optimization, all that sort of stuff that help us to find the solution. When this solution is found, we map the solution back to the real world. So the whole thing about modeling is that we find this way from the problem to the solution for the risk-free space where we can do anything and at, well, almost zero cost. A frequently asked question, especially from industry people, is should we actually trust the model, or why should we trust your model, or why should we invest into building the model of the system? Well, indeed, as I'm saying, this process is not formalized. It's no science behind it. Therefore, all models are actually nothing but limited representation of reality. And therefore, well, it's kind of well-known sentence, all models are wrong. Okay? One talking about like validation or verification of the model. It's in a way, all these things do not make sense as long as this is already kind of wrong, simplified thing. But by the way, these are direct quotations from John Sterman, and I recommend this book. It's called Business Dynamics. It's a famous book by John Sterman. It's probably one of the best books on modeling in general. The, let's say, technology that's used there, it's called system dynamics, maybe of not directly applicable to your problems, but the, let's say, general philosophy of modeling is very well described there. So then why modeling? The thing is that you'll have to make a decision anyway. When, let's say, building a container terminal, when deciding on how many people will be working at this particular warehouse, etc. So decision will be made anyway. And if you think, how actually do people make decisions in the real life? In many different ways. In many cases, they just use their, intuition, experience, etc. And that means that they use their mental models that are in their heads. So the whole thing about modeling is that not whether to use the model or not, but which model to use. So important thing, if you at the end of the day, when you walk out of this room, is that if you just remember that simulation modeling is just yet one more way to be a little bit more informed about system when you're making decisions. It's not kind of silver bullet. It's not gonna help you to solve all your problems, but it'll help you to get a little bit more insight into the how things work, into what kind of behavior or dependencies may be there in the system you're dealing with. Types of models. Mental models. These are the models that are in our head. We're used like every day when making decisions, like change road when you're driving, or choose the route from home to work, or which tone to use when you're talking to your employee or boss, etc., etc. These are kind of mental models that are, your heads are full of them. A little bit about terminology. Like in English, when you say model, it can mean any way. Like if you draw an org chart of organization on a sheet of paper or in like Visio or PowerPoint, that's still a model. And you can do very simple things like, change these boxes and see what kind of structures appear there. So that kind of stuff is also called model. Yeah, physical models like a toy railroad or maybe a wind tube which is used when they design airplanes would be examples. When you're in like high school and you learn physics, all these formulas and Newton laws, etc., are nothing but analytical models of physical reality. Excel spreadsheets with calculations are also models, and at the end there are simulation models where something is happening, something dynamic is happening. Okay, so let's say if you visit like 100 companies, big or medium, and you visit their optimization or strategic planning departments, and you look at the screens of the people working there. So what will be the simulation, or let's say the modeling tool, not the simulation, modeling tool number one? What do you think it is?
Excel.
Correct, absolutely. In business, like 80% of the models are done in Excel. Well, the reasons are obvious because Excel is everywhere, it's on every machine, everybody knows how to use it, more or less. So it's very accessible, it's kind of intuitive, well, at least until a certain level. And if it works, that's fine. But how does Excel actually work? You have certain cells with your inputs, you have other cells with your outputs, and you have some functional dependencies between outputs and inputs, be it like formulas, or maybe in advanced cases that could be like scripts written in Visual Basic, so either direct analytical or a little bit more complicated algorithmic dependency between output and input. So that's all Excel does, and it helps in many, many cases. However, analytical solution, or let's say Excel type of models, is possible when the size of the problem is really manageable. And what probably is more important is that the behavior of the system you're trying to model is intuitive, linear. You can well map it to this is my output, this is my input, this is how output depends on the input. So if dependencies are clear, then yes, you can build a model like that. However, what if, let's say, in the system you're trying to optimize, you have time and causal dependencies. Example, you're a, like transportation, logistics is a big part of your business. Let's say you have a fleet of rail cars, like a couple of thousands of them, and you need to optimally manage the fleet. When the rail car gets empty at a certain station, you need to decide where to send it, here or there, etc. So when you try to build that kind of models in Excel, you're inevitably hitting the limits of analytical modeling because, okay, you're sending this car, today it's here, if you send it there, it'll arrive there in like 2 or maybe 3 days, then while it's there, etc., etc. So things happen in time. System is essentially dynamic. There are like time and causal dependencies do matter. And people actually try to build or try to to describe those things in tools like Excel, they fail. I've seen, let's say, hundreds of huge, formidable Excel spreadsheets with a whole lot of scripts behind them, trying to deal with dynamic nonlinear systems. And actually, time spent on developing these monsters is huge. Output is really a very low value. It's impossible to manage those things or to communicate them. So the thing is, for the systems like that with nonlinear behavior, non-obvious dependencies of output from inputs, with stochastics and uncertainty. In other words, for dynamic, essentially dynamic systems where time matters, simulation modeling does make sense. Example: let's say you have a bank, like a simple, like I don't know, like Savings Bank of Russia, just a typical office. Let's say, very simplistic case: 10 clients per hour, one teller at the counter. Mean service time is 5 minutes. What's the mean waiting time in the queue, or what's the queue size? That kind of questions you may ask. There is analytic solution indeed, like so-called Little's law. So and you can find it very easily. It's based on certain assumptions of how people come to the bank and how are they served. But this assumption, well, it's exponential distribution, but if you don't know what it is, just don't worry, we will probably be going through that stuff later on. In reality, if you think how the bank works, the service time is never distributed like that, because it's probably something like this. There are many people with, like say, short operations, like cash a check or whatever, and there are few people with more complex transactions, like open an account, close an account, etc. So service time is distributed like that. So if you relax this assumption, then you still probably will be able to find the formula. It will be already a little bit more complicated. But what if there are, let's say, not one teller, but many of them? The analytic solutions grow bigger and bigger, and at the end, for a real bank where, where the like business processes are really a little bit more complicated than what I described, and the service times are distributed, let's say, arbitrary, there is no analytic solution at all. And the thing is that simulation model for that kind of thing can be built in like 5 minutes, and I'll be showing later on, and immediately gives you the answer, immediately. And it's free of all these assumptions which underlie formulas. So what is the simulation model? With Excel model or analytical type models, you say calculate. With simulation models, you say run. Simulation model is essentially an executable model. It's actually a set of rules that allow you to obtain the next state of the system in time, given the current state. So any simulation tool, what it does, it builds you the trajectory of the system in time based on certain rules described in the model. So as well as, let's say, Excel spreadsheet, simulation model does have a certain input parameters. But instead of calculating the results, it will simulate, it will build the trajectory of the system in time, and the outputs of the simulation model are observed like these Y's, are observed as the system is being. This is, well, by no means it is a complete, but pretty representative set of areas where simulation modeling is widely used and where it has accumulated a lot of what we call success stories or whatever. The application areas are located here on the abstraction level scale of the underlying models. So down here we have very detailed models where we do capture a lot of things and we like do model individual objects, sizes, velocities, meters and seconds, physical interaction, etc., etc., etc. Example, pedestrian flows, like evacuation of a sports stadium. Control system, let's say ABS system in a car. Up there are abstract models. Models where we throw away a lot of things. We may not think in terms of like individual objects, we may think of how many are there. Reasoning goes in terms of like influences, trends, how this global variable affects that one, etc., etc. And there's a whole lot of abstraction levels in the middle. So the notion of abstraction level, many details, few details, matters a lot. In any simulation project, the right choice of your abstraction level, what's in, what's out of scope of the model, is very important and maybe really critical for the success of a simulation. Methods. To date, there are 3 methods. By method, I mean language, terms, methodology, how you actually map your system to the create the image of the real system in the world of models. There's what's most commonly known, probably, so-called discrete event simulation or discrete event modeling or process-based modeling. Anybody is familiar with that? Yeah. Okay, one, all right, good enough. Another term, which is more used at strategic level, consultants who do services for company managers use this a lot, the system dynamics. Anybody is familiar with the term system dynamics? One. Perfect. And there's agent-based modeling. It's the newer stuff. So these two are like 50, 60 years old. This is newer, like 10 years old method. So, anybody knows this? Heard of this? All right. So, what I'll do now, I'll introduce you to these 3 methods, and this is actually all that, let's say, complete set of methods, so all methodology that you do have in simulation modeling to date. And we will build a system dynamics model, a discrete event model, and we will play with one agent-based model and probably discuss things, how they actually work. And this is the plan before we make a break.